Those written prelims in grad school, by the way, were really tough exams. They were 4-hour exams. They were the toughest exams I ever took. But I made it. Also have an outline of the proof that if the coefficients are from a field, the polynomial ring is a principal ideal domain, PID. F is a field. By the way, I've said this before, I'll say it again. Maybe this could show up on the next quiz. Even if F is a field, the coefficients are from a field, this ring is never a field. This polynomial ring, it is a ring, but that's not a field. There are plenty of things in there that are not units, anything with degree greater than or equal to 1. Okay, that's worth remembering. But it is a PID, principal ideal domain. I have mentioned that before as well. It's an analog of a cyclic group. It is assumed to be an integral domain, first of all, in which every ideal is a principal ideal, just like cyclic groups are generated by one element, and every subgroup is a cyclic group. Every ideal in a PID, principal ideal domain, is in fact a principal ideal of this form. Again, this is technically a different concept than a cyclic group, and in fact, in general, does not equal the cyclic group generated by A under addition. It's a similar kind of concept, and we use the same kind of notation. I think I did mention this once. I'll mention it again, but probably not again after this point. In other books, this notation is actually a little different. Some people use this notation instead. Just as a word of warning in case you're ever reading another abstract algebra book where it gives that notation for both cyclic groups and principal ideals. So again, PID, principal ideal domain, is an integral domain. It's assumed to be an integral domain, first of all, in which every ideal is of this form. And PIDs, therefore, like cyclic groups, are relatively simple compared to other rings. That's the idea. Here's an outline of the proof. What do you need to show? Well, first, it shouldn't have any zero divisors, but we already knew that. We already know it's an integral domain, because if F was just an integral domain, we've already seen that Fx would also be an integral domain, no zero divisors. So we need to show every ideal is a principal ideal. Let A be an ideal in this ring. If A is trivial, then A is the principal ideal, generated by 0. Otherwise, if A is not just 0, if it's not trivial, there will be some polynomial in A that's got minimum degree. That minimum degree could be 0. A could contain constant polynomials. Remember again, 0 has an undefined degree, so even if it contains 0, it doesn't mean the minimum degree is 0. Maybe it contains no other constant polynomials but 0. Maybe the minimum degree is 1. It's got a linear polynomial. Maybe the minimum degree is 2. It's got a quadratic but nothing lower degree. The claim is that any polynomial minimum degree will generate A. That would need to then be proved. Certainly, the principal ideal generated by G is a subset of A, a sub-ideal of A. Why? Since A is an ideal containing G of X. It isn't really that trivial, though that's again one of the things that's almost so trivial that it's confusing. Certainly G of X is in A, by definition of what G of X is. Since A is an ideal, it's again superclosed under multiplication. Anything in here is something in the ring times G of X. That arbitrary thing in the ring times g of x is going to be an A, because A is superclosed. Multiplication. So this definitely is a subset of A. God, now you can think in terms of set inclusions, but it is a pretty quick verification. What about the other direction? Why is A a subset of the principal ideal generated by G? That's where you have to do a little bit of work. Suppose you've got an arbitrary thing in A. This is a common thing to do. Go ahead and apply the division algorithm to that thing. Divide it. Go ahead and divide it by G of x and see what happens, so to speak. Now, again, it's an abstract argument here, so you don't have specific examples that you're actually doing calculations for, but you know by the division algorithm that there would exist a q of x and an r of x, such that f of x would be q of x times g of x plus r of x, where r of x either equals 0, is the 0 polynomial, or the degree of r is less than the degree of what you were dividing by, less than or equal to. Well, actually, strict less than. Strict less than the thing you were, degree of the thing you were dividing by. The degree of G is minimal in A, and this equation would imply R would be in A, because R would be f of x minus q of x times g of x. This is going to be in A, and this is going to be in A by assumption. Since, again, the degree of G is minimal, R has a degree less than G, or it's 0, it's got to be 0. Say it again. The degree of G is minimal in A. We know from the division algorithm that the degree of R would be less than the degree of G. It can't be in A, then, unless it's the 0 polynomial. It's got to be 0. Therefore, this is true, which would mean f of x is a polynomial multiple of G. It's in the principal ideal generated by G. By definition of principal ideal generated by math. I think this could be exam level if I gave you some hints too. So it's definitely worth studying. I'm going to skip this for the moment, and also this slide. You've seen these slides before. All right, let's get into more depth in chapter 17 in the time we have remaining. We've talked about irreducibility over a field. Irreducibility and reducibility, really, because they are opposite concepts. If it's not irreducible over the given field, then it is reducible, and vice versa. But you can actually define these things, these ideas, over integral domains, but the definition is a bit trickier. Maybe for time's sake, I'm going to need to go faster than you might be able to write here. Maybe it's best to just listen and just write down the names of things, or what we're defining. And you can write down, for example, that I'm about to define, go through the definition of irreducibility and reducibility over an integral domain on page 289. Chapter 17 open at the same time. Suppose you have an integral domain and a polynomial with coefficients in the integral domain that is neither the 0 polynomial nor a unit. And as you think about this definition, imagine D is Z. Doesn't have to be Z, but it very well could be Z. And so we could be talking about that polynomial ring. The units in there are pretty simple. There are only 2 of them, plus or minus 1. The constant polynomials plus or minus 1 are the only units in Z of x. They're the only things that have multiplicative inverses. They're both their own multiplicative inverse. Nothing else is a unit. So we're talking, if D is Z, we're talking about non-zero polynomials that are not plus or minus 1 either, but they can be anything else. It's said to be irreducible over D if, this is the confusing part here, whenever f of x is expressed as a product, f of x equals g of x times h of x in dx, then g or h is a unit. Kind of a confusing definition. On the flip side, a non-zero, non-unit element of d of x that is not irreducible is said to be reducible over D. And again, you should always say the over D. Even though it's confusing, it should seem a little familiar. How? Being irreducible over an integral domain is analogous to being prime. What does it mean to be a prime number? It means when you're written as a product. Imagine these are numbers. This number equals this number times that number. Whenever that happens, when this is prime, either g or h is going to be 1. We typically think about positive numbers, but here if we're thinking in z including negative numbers, it could be plus or minus 1, because those are the units in z. Anytime you write a prime number as a product of two numbers, two integers, one or the other of them has to be plus or minus 1. The units of z. It's analogous to it. As we already discussed, when the integral domain is actually a field, then this definition, it's a little bit more natural way to think about it. A non-constant polynomial is irreducible over the field if it cannot be expressed as a product of two polynomials of lower degree in the field. Meaning, neither of those two polynomials is a constant, by the way. Because if one of them was constant, then one would have the same, the other one would have the same degree as f. Tracking with me here? You guys were energetic at the beginning of the class today. This is, being irreducible over a field is analogous to being prime. Being reducible is analogous to being composite, not prime. They're similar concepts. Here are the examples from your book. 2x squared plus 4 is irreducible over Q, but reducible over Z. Q is a field, Z is not, but Z is an integral domain. Now, in either Q or Z of x, we can do this factorization. Q is a field. Q is a field. I have not factored this over Q of x as a product of two polynomials with lower degree in Q. It's irreducible over Q. It's impossible, in fact. The roots of this are going to be, the ultimate factorization of this is going to be 2 times x plus root 2i times x minus root 2i, where I is the complex unit, imaginary unit here. You should be careful saying that word unit. This thing. That's the ultimate factorization of it. It doesn't have any roots in Q. It is degree 2. It's got to be irreducible over Q. Q is a field. But it's reducible over Z. Why? To be irreducible means whenever you're written this way, one or the other, it's got to be a unit in here. But neither of these are units in ZX. 2 is a unit in QX, but not in ZX. In ZX, neither of those is a unit. So it's not satisfying the condition for being irreducible over Z. It's therefore reducible over Z. Two is not a plus or minus 1 in Z, so to speak. But it is a plus or minus 1 in Q. Well, yes, in the sense that it is a unit. I'm talking about units here. Plus or minus 1 are units in Z. They are also units in Q, but there are plenty of other units in Q. All non-zero numbers are units in Q. Q is a field. The same polynomial is irreducible still over R, but reducible over C. R and C are both fields. In R, I can't go any further with this factorization. It's still irreducible over R. But I can write this factorization with these polynomials being in CX. Polynomials with coefficients that are complex. So it's reducible over C. So it's a little strange here. We go from reducible to irreducible to irreducible to reducible as the field keeps getting bigger, so to speak, but again, Z is not a field, as the ring keeps getting bigger. X squared minus 2 is irreducible over Q, but reducible over R. You can factor it over R like this. But square root of 2 is not rational, so it's irreducible over Q. And here's another example. Now we're talking about over finite fields. X squared plus 1 is irreducible over Z3, but reducible over Z5. We could use the test we talked about already, the degree 2 or 3 test. If it's going to be irreducible over Z3, that must mean it's got no roots in Z3, no zeros. If it's going to be reducible over Z5, it must have a root, a 0 in Z5. We've already checked it over Z3. We've done that already. Right? We did that last Friday. It's also technically on your quiz, though you didn't have to check it. Over Z5, it's reducible, though. There must be some root in Z5. In Z5, f of 0, 0 squared plus 1 is 1, which is not 0. That's not on 0. F of 1 is also not 0. F of 2 is 2 squared plus 1 is 5. That is a 0 mod 5. 2 is a 0. Is 2 the only 0? Theoretically, it could be. This could be factorable as x minus 2 quantity squared, which in Z5 would be x plus 3 quantity squared. But probably not. Let's just see what happens. F of 3 is 3 squared plus 1 is 10. That's a 0. 4 should not be a 0, though. This should only have 2 zeros. Z5 is a field. You're going to have, and this quadratic is degree 2, you're going to have at most 2 zeros in Z5. So 4 should not be a 0. And indeed, it is not. It equals 2 mod 5. F of 4 equals 2 mod 5. Evidently, x minus 2 times x minus 3 is a factorization of x squared plus 1. Well, what do I really mean here? I really mean x plus 3 times x plus 2 mod 5. X squared plus 2x plus 3x plus 6 mod by 5. This becomes 0. This becomes 1. X plus 3 times x plus 2 is a factorization of x squared plus 1 over Z5. It's reducible. Got to go quickly over the next few slides. You really should do examples with these slides. The book's got examples. I don't have time to today. We will do some examples on Wednesday. Again, don't write these down, these next few slides. Just listen. Here's some more facts, the first of which we've already got, the degree 2 or 3 test. Only works for a field, though. It's got to be a polynomial of degree 2 or 3. Then f is irreducible over capital F if and only if it's got a 0 in capital F. If capital F is a field and if the degree of f of x is 2 or 3. Here's a fact that is in the textbook. It's a little bit surprising looking at it. And the proof is kind of confusing. If you've read chapter 17 carefully, you might remember stuff about the content of a polynomial and primitive polynomials. I always find that the proof of this especially to be confusing. It's not super hard actually, but it's just confusing. Let f be a polynomial with coefficients in z. If f is reducible over q, it can be written, since q is a field, as the product of two polynomials of lower degree with coefficients in q. It's also reducible over z. You can actually factor it as a product of things, neither of which is a unit over z. So maybe more useful is actually the contrapositive of this. If it's irreducible over z, then it's also irreducible over q. Expanding, if your coefficients are in z and you expand your ring from z to q, it doesn't really help. Trying to factor it doesn't really help in terms of factoring. If you expand your ring from z to q when your coefficients start out in z. Other kinds of expansions of the ring can happen. Like expanding from r to c, for example, helps you find roots of x squared plus 1. Plus or minus I. If you go from z to q, it's not as helpful. It's kind of the gist of this. Something called the Rational Root Theorem. I think I'll let you look at that, and you should look at it before class on Wednesday. I'm not going to talk about it right now, so I'm going to get to the next slide. Mod P irreducibility test and Eisenstein's criterion. But you can't read Eisenstein without thinking Einstein. But they're not related. And Eisenstein actually came before Einstein. Okay, Eisenstein was in the early to mid 1800s. Einstein wasn't until the late 1800s, early 1900s. Through the mid 1900s. I don't think they're related. Their names aren't the same anyway, they're just similar. The mod P irreducibility test, besides the degree 2 or 3 test, is probably the most useful. And it's related to that homomorphism I was talking about in lecture 8. Let P be a prime, and let f of x be a polynomial with coefficients in z. That's not constant. Degree greater than or equal to 1. Let f bar, notice the bar there, of x be a polynomial in zp, p is prime, obtained from f of x by reducing the coefficients of f mod p. Essentially applying that homomorphism. That ring homomorphism I mentioned in lecture 8. From z of x to zpx. The natural one where you apply it to all the coefficients. You're modding them all by p, or p is prime. If f bar is irreducible over zp, which you might, certainly if the degree of f is 2 or 3, is easy to check by plugging in numbers from zp and doing mod p arithmetic. If the degree is 4 or higher, it's harder. And if the degree of f bar has not gone down, in other words, the leading coefficient is not divisible by p, so you don't get 0 mod p. The degree is the same here. Then f of x is also irreducible, interestingly enough, over q. It's not a typo, there's a z here and a q there. We are mostly interested, as far as the theory of factorization, in polynomials in z. But we might need to be thinking about whether they're irreducible or not over q. This is probably, along with the degree 2 or 3 one, the most useful fact in this chapter. This has lots of applications. It's not always going to be something that's helpful, but many times it is. Book's got examples. What's Eisenstein's criterion? It says this. It's kind of an odd theorem. Suppose you got a polynomial with coefficients in z, and suppose you can find a prime with these properties. P does not divide the leading coefficient. That's a not divide there. But it does divide all the other coefficients. But P squared does not divide the constant term. Then f of x is irreducible over Q. Kind of a strange little theorem. You might wonder how applicable it is. Is it, when would this happen? Maybe not real often. But it's worth talking about and reading about and practicing a little bit. It's once in a while, I'll say. All right, see you on Wednesday.